The built environments shelters us from the weather and all that stuff, keep us healthy, happy, and able to focus and able to function with like good indoor air quality and stuff like that. So ASHRAE is one of these groups of people who are coming up with these standards. And ASHRAE 55 is on thermal comfort. They've set standards for thermal comfort for designers to reference, so we can have this repeatable level that everybody needs to meet. So here's one of your quiz questions. List parameters that impact thermal comfort. So the main thing is, remember that ASHRAE 55 is about thermal comfort, and then we're going to discuss how designers predict overall thermal comfort. So again, ASHRAE 55, thermal comfort. The core of the standard specifies methods to determine thermal environmental conditions in buildings and other spaces. So this is something that helps engineers make design decisions that can achieve a reasonable amount of thermal comfort for the majority of people. There's always going to be outliers in a building, people who are not comfortable inside the set temperature ranges, stuff like that. You know, there's always going to be somebody who's uncomfortable, but this allows them to get a comfort that's acceptable for the majority of the people in the buildings. And ASHRAE standards get updated every 4 to 6 years. They have a winter conference and a summer conference. And at these conferences, industry experts and professionals and researchers and academics and government officials come together and talk about issues, current issues in the built environment, and try to make sure that these standards are up to date and that everything, every issue is being addressed. Like they have a committee for COVID, and I just got an email from ASHRAE saying that one of the things that they've come up with for COVID was the need to flush the air and the whatever, you know, virus, bacteria out of buildings. And in buildings that are starting to reopen, they said that you need to flush the air, 3 air changes out of the building before it's safe again. So if you think about the volume of your house, you know, if you have a 2,000 square foot house or whatever, and the volume of that, it's not that big. It's pretty big though. Think about that compared to some of these institutional buildings on campus, like the library. Think about the air change. A whole air change is the entire volume of a building, right? So if you think about the volume of the library, you have to have 3 air changes flushed out to get all of the contaminants out of a building. That's a lot of air and time and energy to move all of that air out of the building. So at these meetings, you know, there are committees that people join, industry experts and professionals join these committees, and you know, they keep everything up to date and make sure that you know, these standards are where they need to be in terms of environmental conditions and, you know, energy use and technology and stuff like that. So the parameters that impact thermal comfort are temperature, relative humidity, airspeed, operative temperature. So temperature and relative humidity are really closely related, but, you know, what is temperature? Temperature is the measure of kinetic energy, right? We all understand kinetic energy, and when you have molecules that are vibrating, how we quantify that's kinetic energy, and how we quantify that is temperature. Temperature is our experience of that kinetic energy. So when you're in a building and the air, so energy travels from higher concentrations to lower concentrations, right? So when you're inside of a building and the air outside is warmer than your body, you know, the air is made up of gases, and those gas particles are vibrating. It's kinetic energy. That's the temperature of the air. That's how we quantify it. If the air is warmer than your body, then that air is trying to transfer kinetic energy to your body from higher concentrations of energy to lower concentrations of energy. And if the air in whatever room you're in is colder than you are, it's got less energy than you do, and your body's going to lose kinetic energy to the air. So you're going to feel cold. You're losing energy. Temperature is just how we quantify that. Relative humidity is, like I said, temperature and relative humidity are really closely related. Excuse me. So just like in the air and those molecules vibrating, when there's moisture in the air, there is energy in moisture that is in air. And the temperature of the air determines, at any given temperature of air, there is a set amount of moisture that air can hold based on that temperature. So the more moisture you have in the air, the more likely you are to hit to have the higher the dew point. So where humidity condenses, if you have super humid air, then the water is going to condense at a higher temperature. So like if you have a really humid attic and it's vented and your house isn't sealed that well and you're running the air conditioner in your attic, right? If your ducts are not very well insulated and there's really humid air in your attic, what's going to happen? Your ducts are going to sweat. So that's something that you don't want to happen. So that's the humidity level is something that we have to control. And another thing that humidity deals with, our body cools itself down. That's our temperature regulation through sweating. Okay. So when we sweat, you guys understand phase change when you change from like a liquid to a gas, right? And you talked about that in physics. I'm seeing some head nods. Any other head nods? You understand that? Okay. So when you change from water, when you take water and boil it, you're changing water from liquid to a gas. What are you doing when you change water from liquid to a gas? Anyone? What is the process that material has to go through? What do you have to add to water to do that? Heat, yes. So you're adding energy, right? Another way to change phase is to change pressure. And those two things are really closely related. If you take a cup of water and put it inside of, I think they're called Bell cylinders. It's an experiment they do in physics. If you take a cup of water and put it inside of a closed vessel and then suck all the air out of it, you can boil the water that way. You're reducing the pressure. So there's a direct correlation between if phase change and energy transfer. You can either change phase by changing the pressure, or you can add energy to it and it's going to change the pressure. So when we cool ourselves down through sweating, the energy in our body is transferring into our sweat, and our sweat heats up, it evaporates, and it takes that energy with it. That's how we cool down. When it's really humid outside and there's a lot of moisture in the air, it's harder to get that sweat to evaporate. So the more humid it is, the harder it is for you to cool yourself down. And that's why it feels hotter when there's high humidity. If any of you have ever been in a dry environment where there's zero humidity, it can be 100 degrees and it doesn't feel as hot as it does when it's 80 in a really humid environment. So those two things are really closely related. Another thing that affects thermal comfort is airspeed. So air is a gas, right? And it has energy in it. If warm air is blowing over you and it's warmer than your body, it's going to be dumping energy into your body, right? If cold air is flowing over you and it's colder than your body, then you're going to lose energy. So the faster or slower that air moves over you, the faster or slower it transfers energy. So airspeed is another thing that plays a big part in that. And let's see. So lastly is operative temperature, and this incorporates conductive, convective, and radiative heat flow. So like with an electric radiant heater, you're getting radiation. That heat transfers through radiation. It's light, or it's like photons. It's transfer of heat radiation. So we get radiation from the sun, right? So the sun is emitting energy, and that hits the earth. Some of it's broken up in the atmosphere. Some of that light is broken up in the atmosphere. The sunlight that does hit the earth is what transfers its energy to us, whether it's coming through the window in an office. If you're sitting in front of a window and you're sitting in the sun, you're going to feel warmer than if you're sitting in the shade. in an office, or if you're sitting next to, have any of you ever been sitting next to a concrete wall and felt that you felt sort of a chill from that concrete wall? You guys ever experienced that? So that concrete wall, it has high thermal mass, which means it will store a lot of energy. So it's got an energy deficit in relation to how much energy it can store. And so your body is radiating heat energy. And whenever there's an energy deficit, that's the direction in which your body will radiate that energy. And so that's why when you sit next to something with high thermal mass, it feels sort of cold. So yeah. So some other things related to occupant comforts, like your clothing level. You know, your clothes, we use our clothes for insulation, right? Like if you have a down jacket, the insulation in that jacket is created by trapping air and prohibiting that air from moving. You know, air is a pretty decent insulator. Anything that has good insulation properties is a poor conductor of heat. You know, there are foams that you can use for insulation. You can use materials like goose down or fiberglass bat insulation and stuff like that. Goose down and fiberglass bat insulation traps air. And if you'll notice in some of your like down jackets, they're sewed into little squares. That's to keep the air from moving around inside of the jacket. When you have insulation in your wall and your wall is poorly sealed, and air can get into your wall and these convective currents can be created, then energy will transfer into those convective currents and you'll start losing energy to that air. When your wall is sealed properly and that air can't move around in the wall, it has better insulatory properties. But all that being said, like there's lots of different kinds of insulation, but clothes are insulation. Obviously we wear more clothes in the winter and less in the summer. And activity level is another thing that impacts thermal comfort. You know, when you're in a gym and you're running around and exerting a lot of energy, you don't have as many clothes on. It doesn't need to be as warm in that space as it does, say, in like an office, you know, where you're sitting still, you're not exerting a lot of energy. You're going to be wearing more clothes in your office. So all of these things are related to thermal comfort. Make sure I didn't miss anything. I did skip over back to relative humidity. So does anybody know what the specific heat of water is? So in terms of how much energy it takes to change phase of water, specific heat is one way that we measure how much energy you have to put into a substance to get it to change temperature. So it takes 1 BTU. If you're talking about BTUs, it takes 1 BTU, which is about the equivalent to a match or a candle. If you're burning a candle, that's putting off about 1 BTU of energy. It takes 1 BTU to raise 1 pound of water 1 degree Fahrenheit. So when you think about changing phase of water, it takes 1,000 BTUs, a lot more, to evaporate 1 pound of water. So that's just something to think about and to put that into perspective. So moving on, when we're dealing with operative temperature, so we're dealing with convective, conductive, and radiative heat transfer. So operative temperature tries to encompass what the person or what an occupant feels, right? So you have all those different forms of heat transfer, and you can measure all of them in different ways, but they all affect what the occupant is going to be feeling. And so this is a globe thermometer. It's a copper sphere that is painted black so it absorbs as much light as possible. And inside this globe thermometer is a temperature probe that responds to radiant heat gain, loss, and airflow and speed and conduction. So this is how we measure operative temperature. And there are equations that we use to sort of quantify the operative temperature and figure out exactly what we're going to be experiencing. So one thing that designers use is something called the predicted mean vote. All of these environmental factors come into play when you're looking at the predicted mean vote. And this is an index that correlates with what people are going to be experiencing, whether it's cold or comfortable or hot, whatever. And then you can see this formula here shows you, what they use to figure that out. And this is not like some fundamental law of physics. It's very subjective. It's going to depend on the occupants. So, if you're in a rest home, the people in a rest home are going to experience, or they're going to have a different standard for what occupant comfort is versus, kids in elementary school or something like that, that are running around all the time. There's going to be a difference in what they experience as occupant comfort. But like I said, it's very subjective. So the predicted mean vote is then incorporated into something called the percentage of dissatisfied occupants. And to have a good design, engineers want to have their PPD, their percentage of dissatisfied occupants, to be less than 10. So you're trying to design for thermal comfort for, ideally over 90% of the people in a building most of the time. There's always going to be people that are uncomfortable, though. One of the things that I saw, it's sort of a recurring theme. I don't know if you guys have ever heard of Amory Lovins or the Rocky Mountain Institute. He's got a really high performance building, uses a lot of high thermal mass. It's got electric radiant heating in the floors and operable window, automatic operable blinds, operable windows. And, they're trying to reduce their energy use as much as possible. And one thing that he said was that we need to redefine we need to change how we define thermal comfort, as climate change keeps happening, and weather patterns are more extreme, and we're seeing more extremes of hot and cold. We're going to have systems that can deal with this stuff. We're going to have buildings that can deal with this stuff. This might affect the size of our systems in our buildings over time, but at the same time, we have to redefine what we think of as comfortable. So moving on. Again, this predicted mean vote and like the predicted percentage of dissatisfied occupants is something that engineers use as a sort of a standard that they can use to make this stuff repeatable, and it gives them justification for their design. If somebody has a problem with their design, they just point back, this is what I use, this is what everybody uses. So there's a link at the bottom of this page. You can mess with it and see how changing the numbers affect this stuff. But again, this predicted percentage of dissatisfied occupants, it needs to be less than 10%. And there's a link here that you can mess with some of that stuff. So moving on, indoor air quality. So we're going to explain what indoor air quality deals with, list some important factors that impact IAQ. That's another quiz question. Remember what ASHRAE standards address IAQ. Again, ASHRAE is one of the major players in developing these standards, and they've got standards for just about everything in the indoor built environment, or in the built environment in general, from what is good indoor air quality to high performance sequence of operations for HVAC equipment, to how you should structure your network in building automated systems. They've got standards for everything. So IAQ is, this is from the EPA. Indoor air quality refers to the air quality within and around buildings and structures, especially as it relates to the health and comfort of building occupants. So this is centered around occupants. Indoor air quality, IAQ, is occupant centered, not to be confused with indoor environmental quality, which it encompasses more than just the occupants. So when you're looking at interior conditions that need to be more tightly controlled, say if you're in an operating room in a hospital, or if you're in a manufacturing facility or a laboratory, that's where indoor environmental quality comes into play. If you're in an operating room, bacteria and stuff like that is more prone to thrive in a humid and hot environment. So in an operating room, they keep those colder. You want those rooms sterile. So the environmental conditions need to be more closely monitored in a situation like that, because it's vital to the health of the patients. So here's a link for indoor air quality from the EPA. It sort of tells you what their idea of indoor air quality is. The second link deals with mold, which is really important in building science because mold affects not only occupant comfort, it also affects building structural durability and the longevity of the building materials that you use. And then at the last link, ASHRAE's link, shows what some methods that ASHRAE has for achieving and maintaining good indoor air quality. Some important factors, like I said, this is a quiz question, impacting IAQ. Again, moisture. If it's more humid, you're going to have stuff growing. You got mold, durability issues. Humidity, it's harder to sweat and cool yourself down. You know, it makes you feel sticky. The number of people is something that impacts indoor air quality. As far as people goes, people are sources of pollutants, right? So we breathe oxygen, we expel CO2. Anytime you have a gas that is displacing oxygen in an environment, when it gets out of balance, like if you've got more CO2 in a room than you do oxygen, you're not getting enough oxygen, you can't concentrate as well. It's going to affect you. It's going to affect your thoughts and stuff like that. Apparently I'm in a room full of CO2, starting to struggle here. So people also produce moisture, right? When you breathe out, you're expelling moisture from your breath. You know, when you cough, you're coughing moisture particles. And COVID, if you have COVID, you need to wear a mask. You know, we don't want that. And people smell in certain situations. You know, when you're sitting next to somebody and they haven't bathed for a few days, you can smell them. That affects your personal space and your indoor air quality in your space. So as far as CO2 goes, we try to keep this less than 1,000 parts per million, but there are studies that look at the correlation between test performance and ventilation rates. And there's definitely a direct relation between how much ventilation is in a room and how well students do on tests. So we need oxygen to be able to think clearly. And then, temperature, we talked about temperature. Certain ranges promote growth of mold and other unwanted stuff. Obviously, you don't want to be cold, but, when it's warmer and warm and humid, you get weird stuff growing that you don't want to be growing. Humidity, we talked about humidity. Temperature and humidity are very closely related. Remember that. And then chemicals, if you're working in a manufacturing facility, or if you're in the construction lab and you're sawing some like pressure treated lumber, there's chemicals in that stuff, and if you don't have good ventilation, then you're going to be breathing those chemicals in. If you're working in a lab, you need to have plenty of ventilation air to flush that stuff out. And like I said, with COVID and stuff like that, lots of ventilation is key in flushing out those particulates and unwanted bacteria and viruses and stuff like that. The location of the building is going to affect the indoor air quality. If you live right next to a bus stop and you have your window open all the time, you're going to get exhaust fumes from cars and buses and stuff like that. Versus if you live in the country on a farm, and you can open your window and you don't have to deal with stuff like that. Material selection. Have you guys heard of volatile organic compounds? Yes, good. And you guys said you know what LEED is, so you can get LEED points for selecting low VOC materials, right? And a lot of the materials, if you've ever smelled a new car smell, what you're smelling is off-gassing. Those are chemicals that are being emitted by the materials that are in your car. Anytime you smell something, it's from particulates. So there are building materials like in cabinets, you get OSB, pressed woods, some of this synthetic stuff. Some of these things have formaldehyde in them, and they will off-gas. When you go into a house and you smell, after a house has just been built, paint will off-gas. And this stuff is typically not very good for you. You don't want to be smelling this stuff. And if you can smell it, you're breathing it in. You definitely don't want to be breathing this stuff. So there again, ventilation is key. Radon is another thing that impacts indoor air quality. Radon, I'm sure some of you have heard of it, and been exposed to radon mitigation techniques. Like when you're designing a slab, you need to figure out how to design if you're in an area that's prone to radon. Radon is a radioactive gas that sort of just is emitted from the ground, and it's the second leading cause of lung cancer, and it has other potential unknown effects. I mean, it's second to cigarette smoking, and it's a far second, but still, in a lot of these old houses you look at, it's a wonder that none of these people got radon poisoning or got sick from it, but it's because houses used to be built so loosely that air was just able to flow through their crawl spaces and through their houses and stuff, and was able to flush this stuff out. So as our houses get more tight, these are consideration. There's stuff we have to take into consideration. Cooking is another thing. So when you cook stuff, you're breaking down food, right? You're making it easier to digest. So when you change the molecular structure of food, and you're getting oils and stuff out of it, that stuff's going to evaporate. And if any of you have ever worked in the food industry and you look at a hood vent and it's covered in grease and oil and junk, if all that stuff wasn't being sucked out through the hood vents, you'd be breathing that in. And those same things are being emitted when you're cooking a chicken in your frying pan or whatever in your house. All that stuff is coming out of your food. So that's stuff that you have to take into consideration. That affects indoor air quality. And obviously there's lots of other stuff. This chart on the right explains why we want to have our relative humidity around 50%. Again, in hot, humid environments, things that we don't want to thrive will thrive, like mites and bacteria and viruses and fungus, and chemicals are more reactive in higher humidity environments. Below 50% humidity, your mucous membranes start to dry out. If any of you have ever been to a really arid climate, I went to Colorado and my nose dried out and was getting nosebleeds really bad, and it's uncomfortable. Your mucous membranes are drying out, and when that happens in those low humidity environments, you are more susceptible to respiratory infections and stuff like that when your mucous membranes are dry. Obviously, there are exceptions to this 50% humidity rule, and like I talked about in some of these, like in laboratory conditions or industrial environments, manufacturing environments, sometimes you want to have lower or higher humidity, but they have other techniques for dealing with some of this other stuff that goes along with that change in humidity. How are you guys doing so far? Are you following everything I'm saying? Everything okay so far? Any questions or anything like that? Am I boring you to death? Not too bad? Okay. So designing for good indoor air quality. ASHRAE has this guide, and there's a lot of other people that had a hand in creating this guide. You can see there on the slide. But they have a guide for designing for good indoor air quality, and they have this standard that makes designing for good indoor air quality repeatable. And it looks at some of the issues and factors that play a part in buildings and designing for good indoor air quality. Again, lots of professionals are involved with this. And then we have ASHRAE 62.1 and 62.2 help us to determine ventilation rates. So if you guys are interested in HVAC and building energy efficiency and stuff like that, I would recommend becoming a member of ASHRAE. You can be a student member, and they've got a very robust set of documents and information and stuff like that you can access online for free. And you can get on there and you can look at some of these standards in pieces. Some stuff's not fully available, but you can go on there and you can see how designers determine ventilation rates based on the volume of a building and the number of occupants, stuff like that. Structural durability. So again, all of this stuff is sort of related. So we're going to identify building science related factors that impact structural durability. Another quiz question: understand how moisture can impact durability. List ways that moisture hurts a building. Okay, so I've already talked some about rotting, mold, fungal decay. When you have really high moisture contents, like in your crawl space, when you have an unvented crawl space and you have vapor barrier down or something like that, you're not getting as much moisture down there. But when you and if you don't have a vapor barrier, if you have something leaking on top of your vapor barrier and you just have puddles down there, if they didn't do a good job putting that in, or it's sealed too tightly and there's no dehumidification, you'll get mold growing, and it's not good for you, and it's not good for structural durability. Mold will can deteriorate wood and cause it to rot. It will affect the lifespan of lots of materials and finishes. Large temperature swings are another thing that is not good for structural durability. Our houses are designed to shield us from the environment, right? So that being said, our house is always exposed to the environment. So, and when we live in Boone, and sometimes in the fall, we can have huge temperature swings. We can walk to class in the morning and it's, 50, 60 some degrees and it's chilly outside, or, even colder. And you have to wear pants. And then by the end of the day, you're sitting in class in the afternoon and you're sweating your butt off because it's warm outside. You can have pretty big temperature swings. And so when you have two materials, like in structural components or structural connections, when you have two materials that are different and have different thermal expansion properties and expand and contract at different rates, that's typically not a good thing. You can have structural failures from having, huge temperature swings. And a lot of this stuff is not, like how long or not if it's going to fail, but when, when you're dealing with water, especially, there's a lot of building materials out there, like moisture control methods that use adhesives. And, a lot of buildings are designed for like 20 or 30 years, and then you have to start replacing this stuff. So, a lot of the time it's maybe a more simple design is better, but even then, it's not if it will fail, but when. How long is it going to last? And, moisture is one of those things, and large temperature swings is another thing that infects the life of these building products. So window assemblies, for example, here you've got a picture of a window that has ice inside of it. So when you have, there's, I guess, frost, but when you have a double pane window, when you have, say you have a metal window and some sort of a rubberized seal or gasket that's on that window, that metal is going to expand and contract and react to temperature swings more than that rubber seal or gasket. And over time, that stuff's going to fail. So another thing is ultraviolet light. You can see this crack here between these two masonry units here. And there are lots of things that are susceptible to ultraviolet light. If you look at the paint on your car and it's starting to peel and starting to fade, that's ultraviolet light doing that. I was working in the propane industry. We had a certain type of gas line that was susceptible to ultraviolet light. And, code said that we had to cover it in a corrugated drain. And when your termination is at the outside of your house and it's this plastic gas line, and you have ultraviolet, it's susceptible to ultraviolet light. So, you had to cover that gas line and make sure that it was not exposed to UV radiation, or it would deteriorate and eventually fail. But again, some of these plastic and sealants and stuff like that are susceptible to ultraviolet radiation, and it gets everything. If you look at erosion and stuff like that, like Mother Nature is a very powerful force, and nothing will stand up to it forever, right? So we have to design as best we can and cross our T's and dot our I's, and this stuff is important if you want your building to last a long time. So moisture problems. Built-in moisture is a big stressor on a building. So if you're building a house and you have a lot of rain, but you get pressed for time, and you have to, you don't dry in the house fast enough, and you're pressed for time. You have to finish the project. If you don't let the wood and stuff dry out, and you go ahead and seal it up, you're going to have a lot of moisture in your walls. You're going to have moisture seeping out of your wood, and you'll get mold behind your sheetrock or whatever you're using inside your house, stuff like that. Obviously, we have to deal with rain. We spend a lot of time drawing flashing details and moisture management details in our drawings, and then, trying to make sure that stuff is done properly, executed properly on a house. Flooding, obviously, is another issue that we have to deal with. Humidity, as I said before. The ground, depending on what kind of soil is on your site and how you build your footer and your foundation wall and stuff like that. Can anybody tell me what's wrong with this footer here? What's wrong with this picture? What is it missing?
What picture?
What's that?
What picture?
I can't hear you. The footer, like this picture at the bottom of the page. What was that, Charles?
It's missing a drain, right?
Yes. Hydrostatic pressure. The force of water on this wall right here. When you don't detail your drawings properly, and you don't put drainage in, there's no gravel, there's no drain there at the bottom, there's no way for this water to drain, and when you design a wall and you don't take into consideration this hydrostatic pressure that it's going to be experiencing in heavy rains, it could cause failure in this wall. It could cause it to collapse, or it's probably definitely going to crack and start leaking into the basement at some point. But this is all stuff that cause issues with structural durability. So we know that water and humidity and stuff like that causes surface mold, fungal decay, corrosion. You can get if you get a crack in your concrete, it's reinforced concrete, and you get water and whatever else in the salt and stuff in there. You can your rebar will start to rust, and it can cause structural failures. Freeze thaw is another big one. If there's not proper flashing and stuff like that on masonry, and it's not properly done, or you can get moisture in there when you have big temperature swings. It'll freeze and thaw, and then your masonry will crack and fail. So there's a lot of issues with moisture. Another one is capillary action. Can anybody tell me what capillary action is? So like when a sponge soaks up water, that's capillary action, right? So your concrete is porous, and it's the tendency for water to be drawn into something like that. So when you pour a slab or something like that, you need to put down a vapor barrier, right, to keep moisture from getting sucked out of the ground up into your slab, and then getting through into your house and creating humidity problems in your basement. Yeah, moisture is a big thing we have to deal with. This is as far as we got in the first class, so